All right, well, let's get going here. So, I guess it's afternoon. Good afternoon, everybody. Thank you for being here. My name is Andrew Skotzko. I'm one of the contributors and one of the core team of Akka.net, which is a project you're going to learn a lot about over the next session. I'm also the co-founder of a company called Petabridge. What we do is we help .NET companies build mission-critical, highly available systems that scale. That's what we do. And we do that by training, consulting, and doing implementation work. So the primary tool we do that with is Akka.net. And so my goal for you today is really to give you an understanding of what this is. So what I want for you today, my wish for you, is I want you to see what's actually possible for yourself, for your team, for your systems, if you embrace the message-based reactivity all the way throughout your system. Not just at little points, but if that's a part of every layer of your stack, what can that open up for you? My goal is that you're going to walk out of this talk today having some new ideas for what kind of systems you can build and what's possible for yourself and for your team. And I also want you to walk out with an understanding of what is the actor model, what is Akka.net, and how can you use that to actually integrate with your existing systems, how can it play well with something like NServiceBus, and how can you combine them together to build something fantastic. So that is my wish for you all. So let's get going here. So let's start by talking about messaging and why do we love messaging so much? And there's a lot of great reasons for this, especially depending on what tools you use. I know one of the people's favorite things about NServiceBus is just how great it is at durable messaging, right? Like we know the messages are going to get there. That's fantastic. But when we think about message-based systems in general, as entire concepts, what opens up for us? For me, it really comes down to two things that I really love. First of all, is that everything's asynchronous and that I'm not blocking myself, that I don't have one component blocking another. I love that. The second thing that I really love, especially as I think about the life cycle of a product and how much a real-world product has to adapt to the market, and as the use cases change and as the customer gives you new requirements and all this sort of stuff, is that we get a loosely coupled system, right? When we have message-based systems, it kind of puts us down a good path for long-term maintainability, which is something I really like. So we have a nicely decoupled system that's loosely coupled, and we can actually build something that works really, really well, but it's also flexible and easily maintainable. And we can have that at every single part of our system. So I think it's fair to say everybody in this room probably loves messaging. Hopefully by the end of this talk, you're going to love it even more. So what would happen if we messaged all the things? If we messaged everything, if it was part of every single component of our system, if we embraced reactivity everywhere? Well, not only would we have all that loose coupling we just talked about, but we would have dramatic throughput increases in our system. We would have a simpler system, a more intuitive system, a more understandable system, a system that we could find and track down bugs in faster, or maybe just write bug-free code, because we never write bugs, but anyways. So to think about what would happen, why is this so important now? We actually have to go back in time a little bit, which is the original title of this talk was Back to the Future, because I had a whole play there. It didn't really work out, but we're going to actually take we're going to go back in time and then catch ourselves up here. So this all really comes down to one word: concurrency. Why do we care? Why have you heard so much about concurrency, about actors, about things like this over the last 12 to 24 months? 4 years ago, this wasn't a thing you were hearing about all the time, but I'm guessing you guys have probably all seen a lot of this stuff lately, and you're kind of maybe wondering a little bit like, what's the deal? What's going on? Why is this? Why now? Right? What's going on? So let's figure that out. Let's go back in time, 1973 through 2005. What's happening? Well, we're flying. Everything's smooth. It's easy. Moore's law is in full effect. Every 18 months, all of our stuff gets faster, and we didn't have to do anything. It's free lunch. It's beautiful. We love this. Everything gets faster. This is perfect, even if you wrote just purely single-threaded code. Well, 2005 rolled around, and my boy Herb Sutter here came to let us know the party is over, people. Well, the reality Herb told us about was that we've kind of maxed out CPUs in their current form factor. We can't really keep increasing the clock speeds without, and fit them into a normal box without melting the damn things. So yeah, they're getting a little bit better throughput increases through larger onboard caches and things like that, but fundamentally, they're not really getting faster. So if we want to do more work, we need more CPUs, right? So that fundamentally puts us into a multi-core world. And if you also look at what's happened over the last, almost 11 years now, since 2005, the internet's like 5 times bigger. Everyone's got cell phones. Everything's faster. Moore's law has kind of faded away. There's more and more happening, and it's happening faster, and we have to do it better. And users have higher expectations than they ever have before. And if we screw it up, we might as well not have been there at all, right? The expectation is a 5-star performance, or you're nothing, right? So if that's the world we're living in, and we've moved to a largely cloud and mobile world, guess what? Whether you like it or not, you're a distributed systems programmer. We all are now. And so we need to think about what are the tools that we have to embrace going forward in this new world. Because the world has changed dramatically, but many people's software has not. Many people are still writing software the way they wrote it in 2001 or 2005, but guess what? It's not 2005 anymore. So we have to change that. If our code is to keep pace with the changes in the real world, something's got to give, and it's going to be our code. Something is going to change. So by now, some of you are thinking this, like, Andrew, what the hell are you talking about, man? Like, seriously, what the hell? And the answer is concurrency. It's time to embrace concurrency. So some of you may not like that idea. Some of you, I saw a couple people back there go like, oh, God. And why might they have that reaction? Well, why is this hard? Why is concurrency hard? Well, let's look at how we do it normally, right? Like, what's the default? How do we do it up till right now, hopefully? Well, you make classes and functions, find some place you can do more than one thing at once, queue some work onto a new thread, maybe off to the thread pool, use some sort of synchronization mechanism, I really hate that word, to protect shared memory. And then finally, we're going to go ahead and finish work on one thread and consume it on another, right? God, there's like a lot going on here, right? Just to do something probably fairly simple. And not only that, but all of this synchronization is expensive. Right? There are real performance impacts to the synchronization. Locks are expensive, guys. And not only on the performance of your code, but on your performance and your throughput as a developer. It slows you down having to figure all this crap out. So my punchline here is that shared state programming sucks. Okay? I don't know anybody who likes it. I only know people who lie that they do. Right? So synchronizing shared state, that's like a pit of doom. That sucks. Coordinating work between threads, nobody's favorite thing. Debugging multi-threaded code, like, yay. Nobody's ever said that, right? Third-party libraries that I'm sure we all use. Are you sure that third-party library is thread safe? And let me just double check, like, how sure are you? Are you sure enough to bet your business on it? Because that's kind of what you're doing. Punchline is that writing great thread-safe code is hard, right? The guys who invented this stuff screw it up. What are us mere mortals to do? So let's think about this for a question. Let's play a little pop quiz here. What were the last two major releases of .NET? What were in them? What was in .NET 4.0? Somebody. That was 4.5. 4.0 was TPL. TPL and async await. Do you think this is random? Does this seem like an accident? You should all be shaking your heads no. This is not an accident. This is not random. Language designers are very smart people, and they saw this coming long before we did, which is why this has been shoved down our throats for almost 6 years now. So hopefully by now, you might be thinking there must be a better way. Like, my God, Andrew, please tell me what it is. And hopefully by the end of this talk, your mind will be blown. This is my goal. And so the answer to that question is the actor model. So what is the actor model? Well, it was invented in 1973 by a guy named Carl Hewitt. He doesn't have very many good photos online, but that's about the best I could find. So Mr. Hewitt here invented this thing. And the punchline is that everything is an actor. The big difference is kind of like we're all used to writing OO code. Everything's an object. Kind of the same idea, but now everything's an actor. In the actor model, the actor is the fundamental unit of concurrency. It's the basic building block of everything, right? You're going to wrap all of your other objects pretty much inside of actors, right? Your DB connections, your repositories, it's all going to be inside of actors. So what is an actor? You're probably wondering. Well, there's a lot of different answers to that question. My favorite way of explaining it is you could kind of think of an actor like a microprocess with a mailbox, okay? Every actor has its own mailbox of serialized messages sitting in it waiting to be processed. And I say microprocess because every actor has a life cycle, right? They can be rebooted, they can be restarted, stopped, et cetera. So that's kind of a good short way of describing what is an actor. It's kind of like a microprocess with a mailbox, and you're going to have a lot of them. So in the actor model, it sounds really complicated, intimidates the hell out of a lot of people. If you have any friends with like neckbeards from Erlang, they've probably made you feel stupid at some point in your life for this. It's actually really simple. And there's only 3 core abilities of an actor in the actor model. Number 1, they send messages. Number 2, they can create other actors. So every actor has a parent. Every actor can be a parent, but doesn't have to be. So they can create other actors. and they can change behavior between messages, right? So if you send me message 1, maybe that, whatever I do as a result of message 1 indicates a new state. I can flip a bit and change into an entirely new state. So basically, actors can be little state machines as well, which is great because you write a lot less code, which is awesome. So congratulations, that's the entire actor model. You've got it. Next time one of your OTP friends wants to get a little smug, you got some ammo here. So we're going to talk about messages first because it's really the basis of everything and is the foundation. So actors work by passing messages. Nothing too fancy here, right? This is pretty straightforward. I think we're all probably used to this. So sending a message, at least in Akka.NET, looks like this. It's just tell my actor your message. Pretty straightforward. So there's other APIs for sending messages, but this is fire and forget. It's called a tell. It's 99.999 something amount of the times you're going to use is going to be a tell. So just know that one. So what else do you need to know about messages? There's two really, really important things you need to know about messages in the actor model and then also specifically in Akka.NET. First of all, messages must be immutable. This is one place that people get a little tripped up at sometimes. This is absolutely essential. Messages must be immutable, so I guess the caution I would say there is just watch out when you're doing collections in your messages. And the second thing to know is that messages are processed serially. So actors have a mailbox and messages come out and get processed one at a time out of that mailbox. And so when you take these two attributes and you combine them with a third property of actors, that's how you get inherent thread safety in your actors. Your actors are inherently thread safe if you basically make your messages immutable. You're good. And that property is the fact that actors have private internal state. Actors do not share state with each other. So if you have an actor and you want to get information from another one, you don't just get to go like reach into it and take it. You have to send it a message, and if it's programmed to, it'll tell you back the information. So the fact that messages are immutable, they're processed serially, and then actors have private internal state means we actually get thread safety out of the box, which is beautiful because it makes our lives scaling out incredibly easy. So that's the first big thing to know about actors is this message property. The second one is that actors can create other actors. Like I said, every actor has a parent, every actor can be a parent. And actors end up living in hierarchies, right? So you have these sort of multi-layered hierarchies here, kind of like an org chart in your company. And this actually ends up being a really, really great thing for us for a couple different reasons. First of all, the actor model is fantastic at atomizing code, at breaking down huge amounts of work into little itty-bitty intuitive pieces. It's great at that. And this is kind of how that happens. You can take a massive amount of data in at the top and break down and down and down. And your actors, when you end up looking at your actual code, very small, very focused, very intuitive, very easy to understand and debug. This is a good thing. The second thing that we like about hierarchies is that this is one of the built-in ways that we get resiliency out of the whole system, right? If you know the roots of Erlang, it came out of trying to build a cell phone network that never crashed. Right? The whole idea is to build a system that never goes down, no matter what happens. And so the way that happens is that, let's say there's an error down here in C4, or C4 over here. Well, the idea is that, yeah, there's going to be problems, there's going to be exceptions. What if we can just capture that and trap it and handle it locally and never let it bubble up to anybody else? Does anybody else care? No. Does anybody else have to stop what they're doing? No. The system just carries right along. We can just reboot C4. Right? Or if it's a different exception, we can handle that differently. So the idea is that we can have very intelligent, localized decision making to prevent faults from taking down the whole system. This is a really, really good thing about hierarchies. So the third thing you need to know about actors is that they change behavior. We talked about this a little bit earlier. And it works a little bit like this. It's called a behavior stack. So there's a stack, and there's a behavior at the top. And whatever's on top of the stack determines how the next message gets processed. Right? This is literally like a block of code that says, what is the behavior to handle the next message? Well, you can change that behavior by pushing a new one onto the stack, or you can revert by popping it off. This is essentially lets you build little FSMs wherever you want them, which is great because you don't have to go write separate ones. So those are the three core things you got to know about an actor. Now, I want to start broadening out a little bit here, and I'm going to be throwing a lot of ideas at you, but I'm also going to leave you some good resources at the end that'll help bring it home for you. So quick show of hands. Who has heard the term location transparency probably a lot lately? Okay, cool, kind of mixed. So location transparency is one of these buzzwords that's going around, especially over the last 12 months. When I say it, what I mean is that you can work with a component in your system and not have to know or actually care where on the network that component lives, right? So a good analogy for location transparency is a cell phone, right? If I want to call my co-founder Aaron, I don't have to know where he is. I don't have to know he's in Dallas or LA or Texas or whatever, or DC. Like, I don't care. I just got to know his number. I call that, it's up to the network between us to make that connection happen, right? That's not my job. I just got to know, have a handle to him, and that's his phone number. Same way with email addresses or URLs, right? The DNS service is basically a giant location transparency service for what server a website's actually running on. That is location transparency. You already know it. The point is, you don't have to know what box the thing is actually on. This is very, very useful. And here's how this actually happens in Akka. So all actors have a globally unique address within an actor system. No two actors can have the same address. This is an example of an Akka address. You know, it has several different components here. And every actor, like I said, globally unique address. But you don't want to have to be thinking about that all the time, because then you don't have location transparency, right? If you have to know it's on this address, on this system, that's just not going to work. So the way we fix this, the way you actually get location transparency is through what's called an actor reference. You can think of this as like a little proxy or a handle to your actual actor. And so basically it's kind of like a black box, where you define how the black box works, but you let the system deploy it for you. And it's up to you, you can configure it, but you don't actually have to worry about where this actor is running. So for example, this actor reference is running on my system user actor name. We'll assume this is on localhost, right? So the way you'll work with this actor is exactly the same as you'll work with this one, which is running on my system at this IP address /user/actor name, right? To you, on the outside of that box, you don't care. All you know is you've got an actor reference, you can work with it. And that's all you have to worry about. And so that property is what gives you very, very easy scale out. Which means that, and this is kind of a big one to take on here, you can write a distributed system on your laptop and scale it out across a bunch of servers without rewriting your code. And you can do it with pretty much only configuration changes. And a lot of the ideas I've been throwing at you here, these all actually, I want to give you an umbrella, kind of like a catch-all bucket to put these in so you can easily come back to it later. It's called the Reactive Manifesto. So the Reactive Manifesto was a manifesto written, I think, in 2008 or 9 by the guys over at TypeSafe, which is a Java company. They invented Akka on the JVM. They also invented the Scala language, so they're very good at what they do. And they wrote this manifesto really about what does the future of our systems as an industry look like. And they really came up with 4 attributes of one of these systems, and they call these systems reactive. And those are, first of all, responsive. It's fast. It's got to be really, really fast. Secondly, it's elastic. So it will stay responsive under varying workloads, right? It'll be responsive at your low hours, and it'll be responsive at your absolute peak load as well, with very little differences between the two, if any at all. Third, it's resilient. It does not crash, despite things going wrong, right? It might be distributed globally around many, many servers, but it doesn't crash. And then finally, it's message-driven, which I don't think I have to really go into here. So this is all part of the Reactive Manifesto. So just start to chew on that a little bit and think about what would happen if everything in my system had those 4 attributes. What if there wasn't a weak point in my system? What if there wasn't a slow service? That'd be pretty cool, right? So by now, you're probably wondering, wait, are we going to talk about Akka.net or what? So we're going to talk about Akka.net right now. So quick show of hands, who has already heard of Akka.net before walking in here today? Oh, good. All right. That makes me happy. Cool. So we're going to talk about Akka.net. What Akka.net is an application framework. It is an unopinionated application framework for building distributed concurrent systems. It doesn't require anything but the CLR. We have full C# support, F# support, and we work on Mono too. And Akka.net is an implementation of the actor model. It's not the actor model itself. It's an implementation of the actor model, okay? And it is a port, an open source port of Akka from the JVM, which is probably the most battle-tested distributed computing framework on the planet. Akka on the JVM has been used by all of these companies and many, many more to handle the heaviest workloads that we've really come up with yet as humans. If any of you have heard of Apache Spark, anybody in here into that stuff? So I know you are, Aaron. You don't count. So if you've heard of Apache Spark and you've heard about all its amazing stream processing magic and all the RDD goodness, this is where it gets it. That's powered by Akka. So you can build some incredibly powerful things with this system. And the reason I show you this slide is A, to impress you a little bit, but B, to show you that the ideas in here have been incredibly well vetted. These have been incredibly well battle tested, and they have stood the test of time. So I just want you to know that. So let's get into Akka.net specifically at this point. So this is an actor. This is what an actor looks like. This is about the simplest actor you can have. You inherit from untyped actor, which is the base actor of everything, and then you write your own message handling code. And that is all you have to do. Out of the box, you get all kinds of location transparency, you get restarts, you get supervision, does all that heavy lifting for you. You just have to decide how you want to process your messages. Now, speaking of messages, what do those look like? These are messages. They're just POCOs, whatever you want. It can be empty, it can be a string, it can be as complicated as you want, up to you. Right? Nothing too intimidating here, I don't think. So, much to the chagrin of everybody who's ever worked on marketing for anything related to Akka or Akka.net, it's not magic. Actors do run on threads. Oh, come on, that's kitties on a treadmill. That's adorable. All right, so the way that works is I mentioned to you that actors have a mailbox, and then they have message processing code. So here's the link between them. This is how you can envision that. There's a mailbox here with messages queued up sequentially that get pushed by a dispatcher into your code. That's what this circle is here. The rectangle around the outside is this invisible fabric called the actor cell. You don't need to worry about it. So the point of all of this is that the framework actually abstracts away all the thread management for you. You don't have to worry about it. You just have to write your code. And it does this one message at a time. So let's talk about a little bit about where can you use this. So like I said, Akka is unopinionated, right? You can build a lot of things with Akka, and we love to see them all. So just a quick sampling, quick buffet of some of the things that I've seen this year out in production. I've seen massively scalable analytic systems. Marketing automation was actually a lot of the roots of the development of the project, was being able to handle massive incoming data streams for millions of concurrent users on mobile devices, and being able to turn around a personalized response to those users in less than a second. With a custom offer. Things like that are very, very possible with something like Akka. Multiplayer games. I've seen a lot of people writing things like this where you would not want a single point of failure. You need a highly available system. Device and Internet of Things tracking. This is one, honestly, we didn't see coming. Probably should have. Been a very, very popular use case, mainly because I think the actor model and the clonability of actors, which we'll talk about in just a little bit, lends itself very well to having many concurrent streams of data and handling each of them as appropriate for that stream. Alerting and monitoring systems, fairly similar to the ones we've already covered. Recommendation engines, something where you need a massively scalable processing cluster. That's something you can easily do in Akka.net if you want to be able to take messages that are coming in, perhaps like off of NServiceBus, and then have a scaled out cluster to handle that stuff and do extra work and recommendations, and maybe you want to do a bunch of machine learning. No problem. It's a great use case. Dynamic pricing, pretty similar to what I just said. Scalable microservices, another one of those buzzwords that's been flying around this year, kind of the same idea. And then another one that doesn't get the love it deserves is reactive UI. If you've ever tried to do reactive UI the normal way, it's kind of a pain in the ass. It's actually really easy with Akka. It does all the work of synchronizing the UI thread for you, makes it quite simple, actually. So maybe you're wondering this. I see a couple people with that like little question mark floating over their head, like, so wait a second. Actors only process one message at a time. Isn't that slow? Like, how is that massively concurrent and fast? Well, it's a good question if you're wondering it, so let me just cover that for you. First of all, actors are really lazy. If there is no work, they do no work. Yes, that is a mailman sleeping in a mailbox. Secondly, actors are cheap. Actors are incredibly cheap resources. They are not sacred cows. You don't need to worry about having many of them. Last we benchmarked it, I think we can have around 2.5 million actors per gigabyte of RAM, which means that some of your scaling problems turn into buy more RAM problems, which is about the nicest kind of scaling problem to have. Actors scale out. There's not an official word for this. I call it clonability. The idea is that you can write an actor class one time and have n number of them scaled out for you in parallel, and the framework will parallelize that for you. So you could have one actor if you're doing, one of the use cases I'm going to talk about here in a second is a fleet tracking system. If you had one like fleet tracking vehicle actor and you had 1 million vehicles in your fleet, you still only had to write one class. So that's pretty cool, the fact that you can have that scale out for you. And then actors are excellent at parallelizing long-running tasks. So if messages are coming in, you can actually kick off tasks onto the thread pool and then keep processing other work and then consume the results of that asynchronous task. So what you can notice in this animation is that the actor's still doing other work while that asynchronous work is completing, and then we pipe it back into the actor or wherever else it's got to go, but you're not blocking. And that's one of the key things. So that is a lot of setup to get us to this point, which is let's start to talk about message buses and actors, specifically NServiceBus and Akka.net. So one of the most common questions we get is, how are they the same? Are they different? Like, we get this question a lot. How do actor systems and service buses, specifically NServiceBus, relate? And well, they're just different. So let's talk about how they're different. It's kind of apples and oranges, frankly. They are both built for distributed systems, but they're for fundamentally different use cases, right? A message bus is really about durable messaging, right? And messaging patterns like pub/sub. Actors they're a concurrency primitive. It's fundamentally about concurrency, not durability. So they're just sort of fundamentally going in different directions, but they actually work really well together. They end up pairing very nicely. And one of the key differences you should be aware of, especially as NServiceBus users, is there is a difference in the default durability of a message. So NServiceBus is amazing for durable messaging. Actor systems by default are not. Actor systems by default, most actor-to-actor communication is in memory, it's in process, and so it isn't durable by default. If you ever wonder about what Akka.NET's defaults are, I can give you a rule of thumb. It's probably whatever's dumb and fast. That's pretty much the way we go. We go for the dumb and fast route, and we have the tools available for you to plug them in where you need them. But there's a big difference in the default durability of messages that you should just be aware of. So we use durability where they need it. So now let's talk about how do these go together? How do these actually pair up? So even though they're fundamentally different, what I think you're going to find as you explore this is that they actually have a ton of shared principles and beliefs. And many of the patterns you already know and love, they're the same patterns, and they extend very easily from NServiceBus into Akka.NET to let you combine the two together and build systems that are highly available and easily, intuitively scalable, and that have durability. So the short answer to how they play together is this. Akka.NET is a great consumer for or producer from NServiceBus. Akka is unopinionated. It does not care where the message comes from or goes to. It's just a toolkit. You can write it to do whatever you want. So this is fundamentally how you can start to pair it up with NServiceBus. One of the common use cases we hear about is people using NServiceBus and then using Akka to rewrite some of the services that are pulling off the bus and doing work. That's a great pattern to follow. So let's talk about some of the shared core beliefs between these two projects. First of all, everything's asynchronous. I think you guys are all very familiar with this. Peer-to-peer mesh. It's kind of, when you think about how these different services combine together, it's kind of like a mesh, right, with named responsibilities. That's very similar. I don't know if you can see that in the background on the slide, but that's very similar to how Akka works as well. You can have scalable clusters of services that work as a peer-to-peer mesh. So it's this exact same idea. Message queues, something you're all intimately familiar with. It's a queue in the service bus world and it ends up in the mailbox in Akka. So it's really all the same ideas. And then finally, extensibility. That's one of everybody's favorite things about NServiceBus, right? It's very extensible, very pluggable. Well, we follow the same model, which I think you'll like. We call it the Home Depot model. The idea being that it's kind of all there and you can just build whatever you want with it. So it's just like there are many, many different modules within Akka. Things to take you over the network, enable clustered applications, to add persistence and durability, and a lot of data modeling stuff for doing CRDTs, if that's your thing. But it's all available, but it's not enforced on you by default. So it's just kind of all available for you to pick and choose as you need. We think you're smart. You'll decide what you need where you need it. So that's something else that the two projects share. So let's talk about messaging patterns, because a lot of them translate. So I'm going to actually show you what I think is probably everybody's favorite pattern, or at least the most common one, which is pub/sub. So we all know what pub/sub is, right? You have subscribers, they subscribe to a publisher, message comes in you want, it gets pushed out to you. Great. So what I want to show you now is actually how simple this is to implement inside of Akka.NET. This is the whole thing right here. You have a hash set of actor references, and then you add or remove from that set, or that hash set as you need, and then when you need to send something out, you just loop over and tell them. That's the whole thing. And what's great about that is you can have pub/sub at every single layer of your application where it makes sense. You don't necessarily have to have it only across services. You can actually have it internal to one service and start to bring that reactivity to the entire service itself. So specifically, though, let's talk about what does Akka.NET give you? Like at the end of the day, why should you as a developer invest your time in bringing this into your NServiceBus system? Why should you care? Well, first of all is reactivity. You're going to have incredibly reactive services, which means speed. You will probably remove any slow service you have. It will no longer be slow. In some of the use cases we've worked on and seen, we've seen 90% plus reductions in average service response times, especially when you're in a high availability environment where you want to have multiple nodes who can service the same request. So that's one great thing is you're going to get reactivity everywhere. You're going to get location transparency. I've probably already beat this one to death, but I'm going to bring it up again. The idea that deployment and location is a configuration detail is absolutely transformative. The idea that you only have to tweak some config to change the entire network topology, it's kind of like a massive idea if you think about that. And being able to scale out just by tweaking some config instead of rewriting your application, that's a big bonus, right? That's a nice way to scale out. Intuitive code. So your code is going to be very simple and very intuitive. This is something else the two projects share. The idea is that it just lets you focus on your domain, right? We share that belief. The actor model in Akka.net, they do a great job of atomizing code. And so, like I said again, you have actors that are very simple, very discrete, very clear. That makes your life a lot better when stuff goes wrong and it's late, right? You're gonna thank yourself that you have simple code when it's 2 in the morning or something. Lowering database contention. This is another one. One of the common use cases that people come to us for is I am absolutely bottlenecked on my database. SQL Server can no longer, I'm just getting killed by write contention or read contention. Well, this is a very easy way, there's a very easy fix for this using the actor model. It's often database contention is fundamentally a data access problem, which you can't really scale your way out of. Because if you just scale it more, you have the same problem but bigger. It's very easy to solve this problem using Akka.net. And then finally, I would say the efficient use of hardware. You're going to actually be more efficient with your capital outlays when you're using this, right? In some of the cases we've worked with, we've seen companies be able to handle their peak workloads with 60% less hardware or 60% less VMs because they're using those machines to their fullest, which is really cool. So one particular case study that I love to think about is this company called Synchromatics, which is a fleet management company. They do city bus fleet and vehicle tracking for a lot of big cities around the country. So like Los Angeles, I think New York, Chicago, you've probably ridden on buses and had your ride tracked by them. That's just the reality. They are a big Akka.net user. And it's been really cool to see what's happened for them over the course of this year as they've been able to change up their system. And they also use queues and service buses. They've seen an 85% reduction in their total code base, which has made their life of training new developers way, way easier and debugging a lot easier because it's 85% less code to learn and it's 85% less code to dig through. So that's a nice thing. 60% reduction in the hardware they need to handle their peak loads, which they seem to really be excited about, or at least their finance people are. And then finally, my favorite quote is that the code just lets us focus on the problem, right? Which is a very similar thing to NServiceBus. The idea is that your job isn't to mess with the framework, it isn't to worry about all these things, it's to solve a problem. And that's what we want to put you in a great position to do. So that's really the intention of all this, is to really just let you focus on your domain and have a very scalable framework underneath you. So what are some of the benefits of the combination of NServiceBus and Akka.net? So I've thrown a lot of new things at you, and I appreciate you guys. I see really good attention, which I really appreciate. So if I were to summarize the benefits of combining these systems together, I would say it's really that you get 3 things, which are not often always found together. You get location transparency, you get durability, and you get easy thread-safe scale-out. Right? You don't have to have lots of complexity to scale out your given services that are pulling off the bus. And you're also going to have your code be simplified. You can simplify procedural code into message-based actor code and have entire Akka services that are asynchronously processing everything off of NServiceBus and doing so in a very, very performant and reactive way. So you're getting the durability that NServiceBus will give you, and you're getting the scalability and the easy concurrency management that Akka will give you. And finally, the idea that deployment of actors is a configuration detail, which I keep saying because I don't think you've gotten how big of a deal that is yet. So. I've thrown a ton of new information at you. What I want to leave you with is a resource, Akka.net Bootcamp. This is a self-paced learning course that we created beginning of the year. We've had something like over 3,000 developers around the world go through it. It assumes you know nothing about the actor model, and that's totally cool. It's free. Go to learnaka.net, and it will take you from nothing up to some pretty substantial levels of building things with. So I just want to leave you with that resource. I see a lot of people taking photos and stuff. The slides are going to be online, so don't worry about all that. They'll go up. And lastly, I just want to say thank you very much. I appreciate your time. I appreciate your attention. Again, my name is Andrew. I'm from Petabridge. We help you guys build highly available systems. And we'll be here all conference. So if you want to talk to us, we'd love to talk to you. So thanks so much for your attention, guys.